Dear ladies and gentlemen, a warm welcome to the Particle Metrix webinar on Multi-Fluorescence Nanoparticle Tracking Analysis, or the next generation EV characterization with the ZetaView instrument family. My name is Dr. Sven Kreutel and I'm working for Particle Metrix as Sales Director. At the beginning, I want to familiarize you with the company Particle Metrix and with its products from the ZetaView product family. Particle Metrix was founded back in 2004 by the physicist Dr. Hanno Wachanik and the sales professional Margret Böck. Both are experts in the field of particle characterization for decades. Particle Metrix has its registered office in Meerbusch near Düsseldorf and its head office with administration, development and production in Inning am Ammersee near Munich. Today, Particle Metrix is not just a German company. Since 2016, we have our own subsidiary in the United States, the Particle Metrix Inc. The headquarters is in Mebane, North Carolina, and we have sales offices in Las Vegas, Dallas, Chicago, and North Yarmouth in Maine. Beside the directly served countries in Europe and the USA, Particle Metrix has a big distribution network supplying all customers from all over the world with our nanoparticle tracking instruments. Most distributors do not only offer a sales department, but also a service organization, allowing us to ensure reaction times less than 48 hours in case of a service call. Since the company was founded, the instruments offered have been continuously developed and improved. Whereas the first ZetaView PMX 100 from 2008 was just able to measure the Zeta Potential of nanoparticles in solution, the next model PMX 110 from 2014 already allowed the measurement of size, concentration and Zeta Potential. Fluorescence, however, is difficult to detect with a PMX 110 due to the relatively faint CCD camera. In 2017, Particle Metrix introduced the next generation of ZetaView instrumentation. The so-called PMX 120 is still the state-of-the-art monolaser NTA system and allows the user to perform simultaneous measurements of particle size, the particle concentration and the Zeta potential of each individual nanoparticle. The use of a highly sophisticated CMOS camera with the PMX 120 now enables the user to detect fluorescence signals according to the used excitation laser wavelength with a very high sensitivity. During the ISEF meeting 2018 in Barcelona, Particle Metrix launched the first in the world two-laser system, the ZetaView Twin. Here two excitation lasers are simultaneously and alignment-free built in an NTA instrument. The switch between the two fluorescent channels is done by a click in the software and in a wink of an eye. This feature allows that all measurements could be performed on the same sample. This also includes the switch between the conventional NTA in scatter mode and the fluorescent mode, as the emission filter can be moved in, software controlled in a split second. The next extension stage of the ZetaView instrument was launched in 2019 during the ISEF meeting in Kyoto in Japan. Particle Metrix doubled the flexibility of the ZetaView Twin by implementing 4 instead of 2 lasers in the same ZetaView housing. This worldwide unique f-NTA technology for the ZetaView Quad enables the user now to evaluate the size, the concentration and the Zeta potential of nanoparticles in scatter mode and in up to 4 fluorescent channels on the same sample in a couple of minutes. It is understood that Particle Metrix plans something new to be available in 2020. Stay curious and follow the latest news on the Particle Metrix website and the corresponding social media. But let's have a closer look into the nanoparticle tracking analysis method used by the Particle Metrix ZetaView. Actually, it is a pretty straightforward technique where you simply inject your diluted sample into the flow cell and visualize the microscopic scatter behavior of the nanoparticles dispersed in the solvent. The ZetaView software then records a set of short video sequences between 0.25 and 45 seconds at each of the 11 positions. Finally, the recording is analyzed for particle movement to calculate the size, the concentration and the Zeta potential. When we have a closer look on the technical and optical setup, we see that we have 1, 2 or 4 lasers located on top of the assembly. An optical element bundles and reflects the laser beam into the quartz glass cuvette or flow cell where the nanoparticles are dispersed in. In a 90-degree angle, a microscope with a 10x objective magnifies the scatter picture of the particles on the sensor of the high sophisticated CMOS camera. A specific software records and analyzes the video. With this setup, the system is able to measure size, concentration and Zeta potential of nanoparticles down to 10 nanometers. A subpopulation analysis based on the different scatter behavior of various nanoparticles is also possible. I will show an example for the label-free separation of a gold, liposome and polystyrene bead mixture later in this talk. By moving a fluorescent emission filter into the scatter light path, the ZetaView is then also able to detect fluorescent signals. In contrast to other NTA instruments on market, which use sample pumps to enhance the number of detections, the ZetaView offers a unique and patented NTA scanning technology, allowing external force-free measurement conditions. Keep in mind that the application of external forces can have a negative influence on the precision of the size measurement as shown by Tong and colleagues in 2015. Anyway, in the ZetaView, the camera as well as the excitation lasers are mounted on movable tables. High precision motors move them synchronously throughout the complete flow cell. They stop automatically at 11 discrete positions within the cell to perform the measurement. At the end, the user gets a representative result over the whole sample volume in the field of view. Additionally, the movement from position to position is so fast that a standard analysis of more than 2,000 to 3,000 particles take less than a minute, including automated outlier control. An asynchronous motion of the excitation laser and the camera, however, allow us to perform fully automated alignment procedures and a user-independent autofocus. Here you see an example why a statistically relevant number of data points is so important when using nanoparticle tracking. Measuring only one position and therefore detecting a low number of data points does not allow a verification if the shown trimodal distribution is real or is it just an artifact. By expanding the measurements to 11 positions in the ZetaView, a statistically relevant number of data points is measured and it becomes clear that the trimodal impression was just due to a lack of statistics. Furthermore, this slide shows us another asset of the 11 position measurement. If you have a closer look on position number 9, you see that there is an optically huge and very bright particle in the field of view. This big guy will lead to false size calculation and also the concentration will be underestimated as the big particle will hide some of the smaller ones. The ZetaView with its automated outlier control will detect the difference in size, concentration and scatter intensity of position number 9 compared to the 10 remaining positions and propose to omit the data from position 9 in the final result. At the end, the researcher has the decision to follow the recommendations or to move on with all 11 positions. But how exactly does the ZetaView measure the size of nanoparticles? In principle, as all NTA instruments, we use the Brownian motion to evaluate the diameter of particles. Keep in mind that the Brownian motion is defined as the random motion of particles suspended in a fluid or a gas resulting only from their collision with the ultra-fast moving molecules of the solvent and not by external forces. So after we took the video, the ZetaView software detects, localizes and tracks all particles in the field of view individually. With this movement information, we can then calculate the mean square displacement of each individual particle, and finally, with the use of the Stokes-Einstein equation, we gain the particle radius. To obtain a statistically robust size distribution out of these individual results, thousands and thousands of particles need to be analyzed. The measurement of the concentration is much easier and does not require any difficult mathematical operation. As mentioned before, we detect and localize all particles in the field of view And of course, we know exactly how big this optical field is. Multiply the field of view with the laser focus plane, give us then the sampled volume of about 3 nanoliters per position. Keep in mind that the ZetaView measures 11 positions, giving a total measured sample volume of about 33 nanoliters. This is compared to other instruments on market about 400 times more sampled volume and explains the superior concentration measuring capabilities of the ZetaView found by Bachurski et al. In a recent independent study. The usable concentration range between 10 to the power of 5 to 10 to the power of 9 of the ZetaView is characterized with a linear relationship between the detected particles and the introduced particles per mil overall 5 orders of magnitude. Last but not least, the ZetaView is also able to measure the zeta potential of each individual particle. Therefore, a voltage is applied between the stainless steel electrodes on both sides of the sample cell. An electrical field established after a couple of milliseconds and the resuspended particles move along the electrical field according to their surface charge. This particle migration is detected for each individual particle by the ZetaView software, whereas the particle velocity is a gauge of the electrophoretic mobility. The zeta potential is finally calculated from the electrophoretic mobility and the Helmholtz-Minkowski theory. But what are the benefits of determining the zeta potential for biological samples such as vesicles or viruses? What could a change in surface charge mean? To give you an idea how useful the zeta potential measurement could be, let's have a look at this little experiment we perform regularly in our lab. Freshly produced liposomes were resuspended in 2 different salt-containing buffers, a high salt buffer with a conductivity of 1000 microsiemens per centimeter and a low salt buffer with a conductivity of 100 microsiemens per centimeter. Both samples were analyzed for their zeta potential using the Particle Metrix ZetaView. The sample from the high salt buffer show a significantly lower zeta potential in red compared to the liposomes resuspended in the low salt buffer in green. However, the differences in zeta potential are not huge, but the simultaneously performed size measurements show a different story. Keep in mind that the axis for the hydrodynamic size is in logarithmic scale, not linear. So the measured size differences are huge and could be explained by aggregation processes of the liposomes that happened in high salt environments. Mutually repellent charges on the surface of the liposomes are shielded by salt ions. This allows the vesicle to come closer and finally aggregate. Taken together, this shows that the zeta potential could be used as an indicator for aggregation processes in a given sample. But let's come back to samples that are more common for biologists and medical professionals. As indicated a few slides ago, I would like to show you how easy it is to distinguish between particles of different material based on their scatter behavior. Some time ago we had a bachelor student in our lab who had the challenge to find a method to separate 60 nanometer gold liposomes and 500 nanometer polystyrene mixed in the same sample. After a couple of days he was pretty frustrated because he was not able to obtain the peaks of the expected particle sizes. Neither the 60 nanometer of the gold nor the 150 nanometer of a typical liposome or even the 500 nanometer of the polystyrene were clearly visible in the size histogram. Finally, he got the hint to use scatter plot projection of the results using the particle size and the scatter intensity. By doing this, it is quite easy to identify the proper population of the corresponding particles. There is a small but very bright population far below 100 nanometer which reflects the gold particles. A second population appears around 150 nanometer and fits nicely with the typical sizes of bio-nanoparticles. And finally, a third population can be found at the upper size scale corresponding to the very large polystyrene particles. However, there are a lot of data points that cannot be clearly assigned to one of the 3 expected groups. Most likely these particles are aggregates and are perhaps composed of more than one particle type. In any case, these undefined agglomerates negatively affect the classical size distribution. When just using the gated particles for plotting the histogram, all expected peaks could be found. Let's briefly come to a short summary of typical ZetaView applications or in which areas the instrument is typically used. On the left-hand side, you see a lot of biological and medical related topics like extracellular vesicles, virus and virus-like particles. But also protein research and drug delivery are huge fields of interest for our nanoparticle tracking analyzer. However, on the right-hand side, you see a lot of technical and industrial applications like polymer research, nanobubbles or quantum dots. In the second part of the presentation, I would like to focus on fluorescent nanoparticle tracking, which currently gain more and more interest among biomedical researchers. The questions which are normally asked by a lot of people is, what type of particles do I have in my sample? Is my nanoparticle really an EV or an exosome? Or is it just a nanobubble, a protein aggregate or an unspecific inorganic salt precipitate? You simply do not know when just using classical scatter-based NTA. And this is the point where fluorescence becomes unavoidable. To understand how the ZetaView deals with fluorescence, you need to understand that we can switch the instrument into two different configurations. The setup on the left describes the scatter mode for conventional NTA. Here the laser beam illuminates the particles and the emitted light in a 90-degree angle is detected by the CMOS camera regardless of whether it is scattered or fluorescent light. Therefore, the total particle count is the count coming from the scatter signals plus the count from the fluorescent signals. When switching to fluorescent mode, a fluorescent emission filter is moved in front of the camera. The excitation laser still illuminates all nanoparticles and the emitted light still travels to the camera, but the filter blocks all scatter information and only the fluorescent signal make their way to the sensor. So the concentration in fluorescent mode is just the signal coming from the fluorescence. When knowing the particle concentration in scatter and fluorescent mode, it is pretty easy to calculate vesicle ratios or biomarker ratios. Basically all modern ZetaView PMX120 instruments available from 2017 onwards are optimized for fluorescence. The single laser systems have one customizable excitation laser of either 405, 488, 520 or 640 nanometer and, if needed, Zeta Potential capabilities. The laser is used for scatter as well as for fluorescent mode, and the wavelength should be chosen according to the desired fluorescent dyes. All monolaser systems come along with a manual fluorescent filter, which can be upgraded to an automated filter changer if necessary. One of the very first fluorescent experiments we made was a membrane stain of extracellular vesicles using cell mass green. The stain preparation was measured first in fluorescent mode to minimize the bleaching effects, followed by the measurement in scatter mode. As the graphs clearly show, we were able to detect about 85% of the particles in fluorescent mode, which means that about 15% of the so far believed EVs were indeed some non-membranous trash. Of course, it is not only possible to use unspecific membrane dyes to evaluate the percentage of membrane-containing particles. You can use fluorescently labeled monoclonal antibodies for phenotyping as well. Here you see two independent EV samples derived from MSC using antibodies against CD63 and CD9. Both were stained with Alexa Fluor 488 and detected with a ZetaView single laser system with a 488 laser. From all present particles in scatter mode, only 11% were detected positively for the CD63 and 2% for the CD9 antibody respectively. A more flexible instrument is the ZetaView Twin, bearing two customizable alignment-free excitation lasers. This special machine offers the researcher the possibility to measure two independent fluorescent channels on the very same sample. It comes along with an automated filter changer and Zeta Potential option. The most interesting system is for sure the 488-640, as this blue-red combination is available in almost all flow cytometers and the corresponding antibodies in your stock could be used as a starting point for f-NTA as well. A very nice and impressive experiment is shown here. EVs derived from the colon cancer cell line HCT116 were stained simultaneously with the unspecific membrane dye cell mask deep red and a mixture of the exosomal markers against the surface proteins CD63, CD81 and CD9. All monoclonal antibodies were labeled with the same Alexa Fluor 488, so it is impossible to distinguish between the signals, but in this case we were just interested in what is called an exosome. The amount of membranous particles was calculated to about 60%, which is pretty consistent with other results. The amount of exosomes could be determined to 45 to 50% of overall particles. But there is more to learn out of this plot. There are rumors out there which claim that NTA is not able to detect exosomes smaller than 100 nanometers. If you look only at the total particle count, then you are absolutely right. Here we cannot see the smaller exosomes as the bigger trash overlays the smaller EVs and the peak size is about 140 nanometers. If you look at the membranous particles stained by cell mask deep red, the peak size already drops to about 110 nanometer. But only looking at the real exosomal fraction stained by the antibodies make clear that this peak size is around 80 to 85 nanometer. This finding is also confirmed by electron microscopy and other methods. Taken all together, it is a matter of what you are looking at, so you need to compare apples with apples. Classical scatter-based NTA is measuring everything in your sample and therefore the size distribution are influenced disproportionately by bigger unspecific particles. However, specific fluorescent-based NTA is able to visualize particles far below 100 nanometer when looking particularly at those vesicles. If you are not interested in the purity of the sample, you can use the free fluorescent channel for a second antibody to double phenotype your vesicles. Here you see an example with an antibody against CD9 and CD81 on MSC-derived EVs. During the ISEF meeting 2019 in Kyoto, Japan, we were the first manufacturer in the world to launch a four-fold laser system. This first instrument of its kind combines 4 simultaneously and alignment-free built-in lasers. The excitation wavelength of 405, 488, 520 and 640 nanometer provide highest flexibility for most of the routinely used fluorescent dyes. As the twin, all ZetaView quad machines come along with an automated filter changer, typical long-pass emission filters and Zeta Potential option. On request, customized bandpass filters and sample recovery option are available. To show the maximum power of the Particle Metrix multi-laser systems, a 4-fold fluorescent labeling with the unspecific membrane-stained cell mask deep red and 3 monoclonal antibodies was performed. As expected for a commercially available EV product, the results show a pretty high concentration of membranous particles. About 93% are positive for the membrane marker cell mask deep red. On the other hand, 21 and 19% of the overall signals are positive for the corresponding markers CD81 and CD63 respectively. Tetraspanin 29, however, seems to be lower abundant compared to the previous mentioned, as only 3% of the overall particles could be identified as positive for CD9. If the purity or the portion of the membranous particles is not of interest, the remaining channel could be used with a 4th antibody. In this example, we included an anti-CD41 antibody to the well-known tetraspanin mix of CD9, CD63 and CD81. 2 types of extracellular vesicles have been phenotyped with this antibody mixture. As the graph clearly shows, there is almost no difference in the detection level of CD9 or CD81. In contrast to that, looking at CD63, a higher number of positives could be observed in the colon cancer cell line HCT116 compared to the MSC-derived vesicles. As expected, EVs positive for the platelet marker CD41 are exclusively present in the blood-derived sample. This result indicates clearly that it is possible to separate and identify vesicles based on the specificity of the fluorescent markers. Most recent results from our R&D lab illustrates that other fluorescent dyes than classical antibodies can be used for f-NTA as well. In this sample we use DAPI to identify nucleic acid containing vesicles. However, it should be mentioned at this point that this result requires experimental repetitions and optimizations, and the number should not be taken as hard facts. If you would like to find more information about possible applications, please visit our application website under particlemetrix.com. When we sum up, we can say that using only scatter mode may provide you with overestimated numbers and concentrations, as you visualize everything that's in your sample, including protein aggregates, nanobubbles, and insoluble salt precipitates. The use of fluorescence, on the other hand, can improve the results drastically as you add specificity to your measurement. Unspecific membrane dyes, such as the cell mask series, DIL or DIO, help with the identification of membranous particles, whereas primary and secondary antibodies allow specific phenotyping of the samples. However, the biggest challenge should not be kept secret. Bleaching is a general characteristic of fluorescence and present in all applications ranging from flow cytometry to fluorescent microscopy. Of course, this also applies to fluorescent nanoparticle tracking. When have a closer look into the different fluorescent dyes, you can identify 3 different types. First, the dye with an ideal photostability, highlighted in green, showing no or only very little bleaching. Data could be recorded easily and without any problems. Second, and in contrast to that, the dyes with the poor photostability in red. Here the signals are lost in milliseconds and reliable data cannot be obtained. And last but not least, there is a broad family of dyes revealing medium photostability. The quality of the data from this group strongly depends on the speed of the data collection and the laser on sample time per measuring position. The ZetaView can acquire reliable data in just 0.5 seconds per measurement position. In most cases, this is short enough to reduce bleaching effects. In NTA instruments requiring longer acquisition times such as 20 seconds or some minutes, bleaching issues are more prominent and reliable data collection might be very difficult. Additionally, we introduced a low bleach technology which is available for all instruments of the ZetaView family. Hard and software adaptations of the machine help to further reduce the negative influence of bleaching effects. As shown in both graphs, the number of detected particles could be increased by around 50% using the low bleach function compared to the standard method without low bleach. In contrast to other NTA instruments with longer exposure times, the low bleach function of the ZetaView can improve the number of detected particles in the fluorescent mode at least by a factor of 2. Taken all together, multi-fluorescent nanoparticle tracking with the Particle Metrix ZetaView allow a broad size range between 10 and 1000 nanometer, a visual representation of the sample for an artifact-free measurement, particles are dispersed in their natural state rather than being immobilized or dried, multi-laser systems offer alignment-free switching of the lasers and the filters in a wink of an eye. The novel low bleach technology enhances the output of all f-NTA applications. The system does not require any expensive consumables. And finally, the ZetaView is absolutely future-proof due to a fully upgradability of lasers, filters and features. At the end, I would like to thank my team and all of our collaboration partners who helped us improving the instrument step by step.